To my channel. I am Dr. KP Naidu. In this lecture, I am going to discuss about one more most important machine learning algorithm that is called as support vector machine. In short form, we are called as a SVM. So in this lecture, I would like to cover the following concepts. What is the main objective of SVM? What is meant by hyperplane, support vectors, margin, what is meant by hard margin, soft margin, different types of SVM, that is linear SVM, non-linear SVM, and kernel trick and different types of kernel trick. Okay, so let us try to understanding these key concepts. These key concepts should helpful a lot while implementing the SVM classification or SVM regression. Okay, while attending the interviews also, okay, they may asking the questions from these concepts only. Okay, the first one is support vector machine. The first thing we all know that, okay, support vector machine is a powerful supervised learning algorithm. That means to build a model using SVM, okay, the data set must be a labeled data. That means the data set must contain a target variable to construct a support vector machine model. Second one is it is used for both classification problems and regression problems, and it is also used for detecting the outliers also. Clear? So that is a second point. Okay, so now another one is it works well in high dimensional space, and it can also handle the non-linear data using the kernel tricks. You can clearly understand this point in the coming slides, in the next slides. Okay, okay, how the SVM uh, handle the non-linear data. Okay, so with the help of the kernel tricks that we will understanding in the later slides. Okay, it works well for high dimensional space and also handle nonlinear data using the concept of kernel trick. Support vector machine are invented by V. Weapin and his co-workers in 1990s in Russia. Okay, so the SVM is mainly or linear classifiers. Just it is just like a linear regression. What we are trying to do is we are trying to find a hyperplane to separate two classes data, that is either positive or negative data. That means separating two classes means it SVM is mainly applied for the binary classification problems. We may also applying the SVM for multi-class classification and binary regression problems also. Okay, but mostly the SVMs are used for two classes problems, that is binary class problems. Okay, so in this lecture we have to mainly focusing on, okay, how the SVM applied for the binary classification problems. The binary classification problem means the target variable contains either positive class or negative class or S class or no class. Okay, either 0 or 1, such type of values we are having in a binary, so target variable. And it is best classifier for text classification also. That is briefly about the support vector machine. Okay, so let us try to understand what is the main objective of SVM means. The main objective of SVM, as already told, okay, the working of support vector machine, it is just like a linear regression. What we are doing in linear regression, we are trying to find the best hyperplane, okay, so to the given points. Okay, so in similar way also, okay, in support vector machine we are trying to find this hyperplane, okay, as like how we are finding in a linear regression. Okay, so apart from this hyperplane we are also find some another type of hyperplanes, that is positive hyperplane and negative hyperplane. Okay, so when we say hyperplane, if the data set contains only two features, we are just finding the straight line. If the data set contains more than two features, okay, then that line we are called as a hyperplane. Okay, the main aim in SVM is to find the best decision boundary or hyperplane that separate the classes in a which one feature space. It may be a some one hyperplane. This apart from this, okay, this hyperplane maximize the margin between closest data points of two classes. Okay, let us briefly understanding what is the statement with some diagrammatic in the next slide. Okay, so hyperplane. What is meant by hyperplane? As we know that, okay, to find out the straight line, to find out the best plane, okay, for example, in two-dimensional data, which equation we are using? Y equal to, we are using the mx plus c, okay. So the same statement we may also sometimes represented as y equals to, okay, beta naught plus beta 1 x. Okay, and the same equation in some textbooks they referred as y equal to theta naught plus theta 1 x. Okay, so in some textbooks, okay, theta naught plus theta 1 x. In some textbooks, the same notation is also represented as y equal to W transpose X plus B, y equal to W transpose X plus B. All these are all are same to find the best hyperplane. To find the best hyperplane. Okay. So here how we are taken as beta and beta 1 or some weights or some coefficient like this. Here also a b and wt, or it may be a b may be a bias. Okay, here the wt may be a some weighted matrix. Clear? So that is hyperplane in n dimensional space is defined by W transpose x plus b equals to 0. That means if we are finding the best hyperplane, that best hyperplane equation is W transpose x plus b equals to 0, where W is a normal vector to hyperplane. Okay, x is the which one? A point in the feature space. B is a which one? A bias. Okay, so how we are representing the vector? Okay, what is the point and what is the bias? Okay, so and how we are finding this hyperplane? I already discussing in the linear regression. Okay, if we are uh, unable to know, unable to find how to calculating that hyperplane, just in the below description I was given that linear regression with example. Just go through that link, then you can easily understanding how to find this line. Okay, so next that is about the hyperplane. Okay, next point is support vector. Okay, so as already told that, okay, so apart from the hyperplane, we can also, okay, find out two more hyperplanes. Two more hyperplanes. These two more hyperplanes we have to find with the concept of which one? Support vectors. Support vectors. Okay. And margin. What's called as margin. The difference between this best hyperplane and this margin is called as the difference. The distance between this hyperplane and this hyperplane is called as which one? Margin. Okay, so here in this diagram I can clearly show, okay, what is support vector. Okay, let us take as this is some two-dimensional, okay, plane I am taken. Let assume this is the best hyperplane. It's called as this is the best hyperplane. Okay, so now from this best hyperplane, let us assume these are all positive classes. Okay, these are all the negative classes. If you are projecting the points in this two-dimensional plane, let us assume we are getting in this area, we are getting all the positive points. In this region we are getting all the negative class points. Clear? So now apart from this hyperplane, in sub SVM, we are also find two more planes. This is another plane. This is another plane. This plane we are representing. Okay, these are all positive classes. Yes. from these positive classes, which class is nearer to this hyperplane? Which class is nearer to this hyperplane? Or which point is closest to this hyperplane? By connecting that point, if you draw the one hyperplane, that is we are called as a positive class hyperplane. Positive class hyperplane. Okay, similar way, this is all our negative class points. Okay, what is the nearest negative class point from this hyperplane? Okay, that is we are called as the negative class hyperplane. That means this is we are called as the negative class hyperplane. Negative class hyperplane. Okay, that means from this hyperplane we are choosing the closest positive point. By connecting that one, we have to draw one hyperplane. This is the nearest or closest negative class point from this hyperplane. By connecting this, we are drawing one more hyperplane. Okay, so this closest points of this hyperplane we are called as the which one? Support vectors. We understood the support vector. The support vector is what are the closest points from this hyperplane. What are the closest points from this hyperplane? Those closest points we are called as which one? Support vectors. We may having any number of the closest points. For example, here we have one positive, one negative. We may also having the more than one also. We may also having the more than one also. Here also we are having three closest points, two positive and one negative. So that means the support vector means the closest points from the hyperplane. Those closest points we are called as the support vectors. Okay, and the distance from this hyperplane to this positive class hyperplane is called as the positive class margin. The distance from this hyperplane to negative class margin. Negative class margin. This distance we are called as the negative class margin. Negative class margin. Okay. So hope understood one more key point in support vector means. Okay. So always we are trying to keep the distance from this margin. This is called an entire margin. This margin must be a maximal. We are trying to find the margin. As you already know that how to find this hyperplane. Apart from that, we are trying to find the positive class hyperplane and negative class hyperplane SVM. Okay, this was called as some margin. Okay, so we are trying to find this margin. That margin must be a maximum. That margin must be one maximum. Okay, so if you're having the maximal margin, then that data set or that algorithm or that if you're getting the maximum margin, then we are getting the good performance from the model. Good performance from the model. For example, if you're getting the some lower distance margin, for example, if we take like this the margin like this, that this distance may be less compared to this distance. So if you are this is the if you're considering this distance, okay, there may be chance to getting the lower performance. Okay, that's why we are trying to find the maximal margin. So how we are finding that maximal margin, we will discuss later in one more lecture with some mathematical concepts. Okay. Now that is about the margin, support vectors, hyperplane, positive class hyperplane, negative class hyperplane. Okay, hope everyone understood some of the basic concepts of support vector machine. This distance is called as the margin. Okay, so now types of the SVM. Types of SVM. There are two types of SVM. One thing is called as linear SVM and non-linear SVM. Linear SVM and non-linear SVM. Linear SVM means we can easily separate the data. This is the positive classes data. This is the negative class data. We can easily separate the data with the help of the hyperplane with some positive class hyperplane and negative class hyperplane. Negative class hyperplane with maximum margin. With maximum margin, if we are separating the data with, we can easily separating the data with some hyperplane and with maximum margin. Then that machine we are called as the linear support vector machine. So the linear SVM is used when the data is linearly separable. Let's see here, this is a positive class data, this is a negative class data. We can easily separate the data by using the hyperplane and with the help of the maximum margin. That's why it is example of which one? Linear SVM. Non-linear SVM. So if you are unable to separate the data, or if you're unable to separate the data, that is we are called as non-linear data. Non-linear data. To this non-linear data also we are applying the SVM. We are applying the which one? SVM with the concept called as the kernel trick. Called as the kernel function. So non-linear SVM is used when the data is non-linearly separable. Here we can see we are having the positive classes and negative classes. If you take as for example, let's take this is hyperplane. Is it possible to separate? Let us assume this is the one. Let's take this is one hyperplane. Is it possible to separate the positive class and negative class? No. Here also some positive classes. Here also having some positive and negative classes. For example, let's take as this is some hyperplane. Let us assume. Is it possible to separate the positive class and negative class? No. Why? Because it is a non-linear data. To solving this non-linear data, so we are also using the non-linear SVM. So for solving the non-linear data, we are using the non-linear SVM. How we are solving that non-linear data with the help of the non-linear SVM means with the help of some concept called as the kernel function. What the kernel function can do is, the kernel function can tries to map this low dimensional data into high dimensional data. Here we are taking some two-dimensional data. If we are trying to converting this two-dimensional data into, for example, some three-dimensional data, then there may be chance to separate the positive class and negative class. That is called as one main concept of which one? Kernel. So what the kernel can do? Map the data into some high dimensional space. That means when we are converting some low dimensional data into high dimensional data, then there is chance to linearly separate the data. Then we can easily find the hyperplane with some maximal margin. That means the kernel trick helps to transform the low dimensional data into high dimensional data. While transforming the low dimensional data into high dimensional data, then the non-linear data may be converted into which one? Linear separable data. That is about the non-linear SVM. Non-linear SVM. So let's see, for example, this is a one more scenario. So let us assume these are the some red class points, and these are some blue class points. It is some binary classification. This is the hyperplane. This is the hyperplane. So we may getting any number of the hyperplane. Yes or not? This is we are choosing one hyperplane. Let us assume, for example, this is also an hyperplane. Yes or not? Separates those two classes. For example, I can take as one more is, this is also another hyperplane. Yes or not? It is also separates the both red class and negative class. For example, I can take this is also some another hyperplane. Yes or not? So for example, I can take as another hyperplane. Maybe this is also some another hyperplane. It divides the both red class and blue classes. That means we having the any number of the hyperplanes to the given data set. But out of all those hyperplane, which hyperplane we are choosing? So we are choosing hyperplane with from which hyperplane we are getting the maximal margin. From which hyperplane we are getting the maximal margin? We are choosing that hyperplane only. we are choosing that hyperplane only. For example, if you are choosing this hyperplane, okay, let us assume this is some red class hyperplane. This may be a some blue class hyperplane. This is the distance, okay, maximal. So this is the margin distance of if you're considering this, if you're considering this hyperplane. Likewise, for example, if you're considering this hyperplane, let us assume if you're considering this hyperplane, okay, this is the red class, maybe red class hyperplane. Okay, we may getting this may be a some blue class hyperplane. We may getting some distance. That's not. That means to each and every hyperplane we are getting some marginal distance. Out of all those marginal distance, from which hyperplane we are getting the maximal margin, that is the best, okay, hyperplane, okay, and that will be give the good performance in support vector machine. Okay, so now here let us consider this is the best hyperplane. Let us show, okay, the equation of this hyperplane, as we already discussed, w2 x plus b equals to 0. If you're getting any test point, okay, if the test point is substitute the into the equation, okay, if the test point gives the positive value, let us assume if your test point gives the positive value, if you are taking any test point, if the test point substitute in the w2 transpose plus x plus b equation, okay, the value of the test point is positive, then that is comes to which one? This class. If you take as any test point, okay, if the test point substitute in this hyperplane equation, if the value is some negative, that the negative means it may be some -2 or it may be -3 or it may be -4, any value with negative, that test points belongs to which one? Negative class. Okay, that means if test points substitute into the hyperplane equation, the result of that equation is positive. That means the test points belongs to which one? Positive class. If the test points substitute into the hyperplane equation, the result of that test point is negative. That means the test points belongs to which one? Negative class. Which one? Negative class. Okay. That is about hyperplane and how to find out the class of the given instance. Okay. So these are all different hyperplanes as we all discussed. From these hyperplanes, from which hyperplane we get in the maximal distance, that is the best hyperplane. Okay, so let us assume this is the hyperplane. Okay, so by choosing this hyperplane, okay, we may getting the maximal margin by covering this point, and here it covers the 2 points. This is called as the maximal margin. Okay, this this is the distance from this hyperplane to red class margin. This is the distance from this hyperplane to this blue class margin. Okay, this is our ultimate goal, to find out the hyperplane with some margin. So what is the advantage of maximal margin? If we are finding the maximal margin, the model may give the good performance.